You know, there's a picture of the atom that everyone carries in their mind. You've seen. It's a tiny solar system. Electrons circling a nucleus like planets around the sun, tracing perfect elliptical paths to empty space. It's elegant. It's intuitive. It makes perfect sense. And it's completely fundamentally wrong. Not wrong in the way a simplified model is incomplete, but wrong in a way that reveals something profound about reality itself. The language we use to describe the everyday world simply does not apply at the scale of atoms. The electron doesn't travel anywhere. It doesn't have a path. And energy doesn't flow the way you think it does. I'm Niels Bohr, and I spent my life trying to explain why the atomic world refuses to behave like the world you see around you. What I discovered, what the evidence forced me to accept, is that nature at its smallest scale operates according to principles so foreign to human intuition that we can barely speak about them without our language collapsing into contradiction. The opposite of a correct statement is a false statement, yes, but the opposite of a profound truth may well be another profound truth, and that's not a puzzle to be solved. That's the structure of reality. Let me start with what seems like a simple question. Where is the electron right now? You might think that's obvious. It's somewhere, doing something, following some trajectory we simply haven't measured yet. After all, everything you've ever seen in your life has a definite position at every moment. The chair you're sitting in doesn't suddenly cease to exist when you close your eyes. The moon is still there even when no one is looking at it. Why should an electron be any different? Here's why. When we actually try to answer that question, when we perform the measurement, we discover something strange. The electron doesn't have a position until you measure it. Not we don't know its position. Not it's hiding somewhere and we haven't found it yet. The electron generally does not possess a definite location before the measurement occurs. And the moment you measure when it is, you destroy any possibility of knowing how fast it's moving. You can't have position or you can't have momentum, but you cannot have both simultaneously. Not because our instruments are crude, but because nature itself does not permit it. This is not a metaphor. This is what the mathematics tells us. And more importantly, this is what every experiment confirms. And yet, our language built over millennia to describe objects with definite properties moving through space has no way to express this reality without sounding paradoxical. So we are forced to say things that seem contradictory. The electron is both here and there. It goes through both slits. It exists in multiple states at once. And all of these statements are true, and all of them are inadequate, and you need all of them to capture what's actually happening. Consider a thought experiment. Imagine you have a single electron and you want to know where it is. You shine light on it to see it, the way you see anything photons bounce off the object and enter your eye. But here's the problem. Light is quantized. It comes in discrete packets, and when a photon hits an electron, it transfers momentum. The very act of seeing where the electron is changes how fast it's moving. You might think, well, use gentler light, lower energy photons. But gentler light has a longer wavelength, and longer wavelengths give you fuzzier images. You can't pinpoint position with blurry light. So you try shorter wavelengths for precision, and now you're hitting electron harder, disturbing its momentum more violently. There is no way out. This isn't a technical limitation of measurement devices. This is nature telling you that position and momentum are complementary properties. You can describe the electron in terms of one or the other, but never both at the same time, and both descriptions are necessary to have a complete picture. And notice what just happened. I used the word complete, but even that's not quite right. There is no complete picture. The wave function gives you probabilities, not certainties. You can calculate the likelihood of finding the electron here or there, moving this fast or that fast, but until you actually measure it, the electron doesn't have those properties. It exists in what we call a superposition A, weighted sum of all possible states. And when you measure, the wave function collapses. One possibility becomes real. The others vanish, not because you disturb the pre-existing condition, but because reality crystallizes at the moment of observation. You want to ask, which is it really? Is the electron a particle or a wave? Does it have a definite position that we simply can't access? Or does it genuinely exist in multiple places at once? And my answer is this: those questions assume a classical framework that doesn't apply. The electron is not a particle in the way a grain of sand is a particle. It's not a wave in the way water ripples are waves. It's something quantum mechanics can describe mathematically, but which has no precise analog in the macroscopic world. Both the particle description and the wave description are indispensable. Both are incomplete, and demanding to know which one is really true is like asking whether light is really vertical or really horizontal. When you measure polarization, the answer depends on how you choose to look, and both perspectives are equally valid and equally partial. Now let me show you where this gets truly strange. You heard of the double-slit experiment. It's the most famous demonstration of quantum weirdness, and for good reason. It reveals the heart of complementarity in the starkest possible terms. Here's the setup. You have a barrier with two narrow slits cut into it, and you fire electrons at it one at a time. On the other side, you have a screen that registers where each electron arrives. Classical intuition says each electron goes through one slit or the other, like a bullet passing through a gap in a fence. You'd expect two bright bands on the screen corresponding to the two slits. But that's not what you see. What you see is an interference pattern, alternating bands of light and dark, exactly like the pattern you get if you send water waves through two slits and let them overlap and interfere with each other. Crests meet crests and amplify. Crests meet troughs and cancel out. But here's the thing. You're sending electrons one at a time. There's no other electron to interfere with. So what's interfering? The only possible answer is that each individual electron interferes with itself. It somehow goes through both slits simultaneously, acts like a wave spreading across space, and then arrives at the screen as a single localized point. Wave and particle at the same time. But now you get clever. You say, I'll watch which slit the electron goes through. You set up detectors at each slit to record the electron's passage. And the moment you do that, the interference pattern vanishes. Now you get two simple bands, exactly what you'd expect from particles taking definite paths. The electron, when observed, behaves like a particle. When not observed, it behaves like a wave. It's as if the electron knows whether you're watching and changes its behavior accordingly. Now I want to be very careful here. It's not that the electron is aware of observation in any conscious sense. This isn't mysticism. The point is that the act of measurement, the physical interaction required to determine which slit the electron passes through, fundamentally changes the system. You cannot observe without interacting, and you cannot interact without altering. The wave function that describes the electron as a superposition of parts collapses into a definite state the moment you measure. And once it has a definite path, it can no longer interfere with itself. Wave behavior and which path information are complementary. You can have one or the other, never both. Not because of experimental limitations, but because that's how nature works. People always want to know what's really happening. Is there some hidden reality beneath the wave function, some deterministic clockwork we simply haven't discovered yet? Einstein certainly thought so. He famously said that God does not play dice. He believed quantum mechanics was incomplete, that there must be hidden variables determining the electron's true position and momentum, variables we simply haven't found yet. And I told him, Einstein, stop telling God what to do. The evidence doesn't support hidden variables. Every test we've devised, every experiment we've run, confirms that the probabilities are irreducible. Nature is fundamentally indeterminate at the quantum scale. But here's what makes this so philosophically devastating. We're not just saying we don't know what the electron is doing between measurements. We're saying the question itself is meaningless. There is no fact of the matter about the electron's position before you measure it. The wave function gives you all the information that exists. And the wave function is a probability distribution, not a description of something definite happening in space and time. Reality at the quantum level is not a collection of objects with properties. It's a collection of potentialities that become actualities only when you measure. And this isn't idle philosophy, this is engineering. Every transistor in your computer relies on quantum tunneling electrons passing through barriers. They classically shouldn't be able to cross because they don't have definite positions on one side or the other until you measure. Lasers were because photons exist in coherent superpositions of states. MRI machines exploit quantum spin-off property with no classical analog, a kind of intrinsic angular momentum that cannot be visualized as anything spinning because it doesn't correspond to motion through space. Yes, satellites must correct for relativistic time dilation. Yes, but the atomic clocks they use depend on quantum transitions between energy levels, discrete jumps, not smooth flows. This isn't speculation, this is tested technology. Billions of quantum measurements happen every second in devices you use every day, and they all confirm the quantum description is correct and the classical picture is wrong. So let's come back to the original misconception, the one that launched this entire conversation. Energy doesn't flow in orbits. The Bohr model, which bears my name and which I myself proposed in 1913, was a stepping stone. It was an attempt to graft quantum ideas onto classical physics, to say that electrons occupy specific orbits with quantized energies, but still move continuously through space. It worked it, explained the hydrogen spectrum beautifully, predicted the right wavelengths of light emitted when electrons jump between levels. But it was never meant to be the final picture. It was a transitional framework, useful for its time, but fundamentally inconsistent. Quantum mechanics matured where Heisenberg and Schrödinger developed their formulations. When we understood wave function and operators and probability amplitudes, we realized the truth. The electron in an atom doesn't orbit. It exists in a cloud of probability described by a wave function that extends through space. You can calculate the likelihood of finding the electron at any given location, but it doesn't have a trajectory. There's no path it follows. And when the electron jumps from one energy level to another, when it emits a photon and drops to a lower state, it doesn't travel through the intervening space. The wave function instantaneously changes from one shape to another. The electron is here and then it's there, with no continuous motion in between. That sounds impossible. It violates every intuition you have about how objects move through space. But that's because electrons aren't objects in the classical sense. They are quantum entities, and quantum entities don't obey the rules of classical mechanics. They don't have definite trajectories. They don't move smoothly from point A to point B. They exist in superpositions of states, and when you measure, one possibility becomes real, chosen according to probabilities given by the wave function. And the extraordinary thing is that this framework, bizarre and counterintuitive as it is, works. Makes predictions that have been verified to astonishing precision. The magnetic moment of the electron, calculated using quantum electrodynamics, agrees with experimental measurements to 12 decimal places. 12. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. But even with all this success, even with the technological revolution quantum mechanics has enabled, there remains the deeper puzzle. What does it all mean? When we say the wave function collapses upon measurement, what exactly is a measurement? Where is the boundary between the quantum system and the classical measuring device? This is the measurement problem, and it's still with us today. I advocated for what became known as the Copenhagen interpretation, the view that the wave function is complete, that probabilities are fundamental, and that the act of measurement is where quantum potentiality becomes classical actuality. But I never claimed this was the whole story. I claimed it was the right way to think about what we can know, given the limits of our language and concepts. You see, this is where complementarity becomes not just a feature of quantum mechanics, but a feature of human knowledge itself. We are part of the universe we are trying to describe. We are made of the same quantum particles whose behavior baffles us. And our brains, our language, our entire conceptual apparatus evolved to navigate a macroscopic world where objects have definite properties and causation is straightforward. When we try to apply those concepts to the quantum realm, they break down. Not because we're stupid, but because we're asking them to do something they were never designed for. And so we find ourselves in a strange position. We have a mathematical framework, quantum mechanics, that describes atomic phenomena with incredible accuracy. We can calculate, predict, manipulate, build. But we struggle to say what it means in plain language, because plain language was built for a different reality. It's like trying to describe color to someone who's been blind from birth. You can give them wavelengths and frequencies. You can tell them about photoreceptors and neural processing. But the qualitative experience, what it's like to see, red remains ineffable. Similarly, we can give you the Schrödinger equation, we can show you the experimental results, but the qualitative nature of quantum reality, what it's like for an electron to exist in superposition, has no classical analog. This is why I insist on complementarity. It's not a failure of understanding on complementarity. It's not a failure of understanding. It's a recognition that reality at the quantum level is richer and stranger than any single classical description can capture. You need the wave picture to understand interference and diffraction. You need the particle picture to understand localized interactions and discrete energy exchanges. Both pictures are indispensable. Both are incomplete. And the truth, if we can even use that word, lies not in choosing one over the other, but in recognizing that both are necessary, contradictory as they may seem. Think of it this way. Imagine you're trying to describe a three-dimensional object to someone who can only perceive two dimensions. You show them a shadow projection of the object onto a flat surface. From one angle, the shadow looks like a circle. From another angle, it looks like a square. The person asks, which is it really? And you say, it's neither and both. The circle and the square are projections of a deeper reality that transcends the two-dimensional space where they appear. Wave and particle are like that projections of quantum reality onto the screen of classical concepts. Each projection reveals something true, but neither is the full story, and you can't see both projections simultaneously because they require incompatible experimental setups. And here's the thing, this isn't just about atoms. This is about the nature of knowledge itself, about what it means to observe, to measure, to know. Classical physics assumed their sharp division between observer and observed. The universe was a great machine, ticking along according to deterministic laws, and though we were outside it, watching, measuring, predicting, without affecting what we measured. Quantum mechanics destroys that picture. The observer is not separate from the observed. The act of measurement is an interaction, a physical process that entangles the measuring device with the system being measured. You cannot step outside the universe and observe it from an objective vantage point. You are part of it. Your measurements are events within it. And that means the universe as it appears to you depends on how you choose to interact with it. This is not subjectivism. I'm not saying reality is whatever you want it to be, or that consciousness creates the physical world. The wave function evolves according to precise mathematical laws. The probabilities it predicts are objective. Everyone who performs the same measurement under the same conditions will get the same statistical distribution of results. What I'm saying is that there are limits to what can be known, not because of human ignorance, but because nature itself is structured in a way that precludes complete knowledge. You can know position or momentum, not both. You can observe wave behavior or particle behavior, not both. And this isn't a defect in quantum mechanics. This is quantum mechanics revealing the deep structure of reality. Now I want to address something that troubles a lot of people. If the electron doesn't have a definite position until you measure it, does that mean reality is somehow created by consciousness? Does the moon disappear when no one is looking? This is a misunderstanding, but an understandable one. The answer is no. Measurement doesn't require a conscious observer. It requires an irreversible physical interaction that entangles the system with its environment. When a photon from the sun strikes an atom on the moon's surface and scatters, that's a measurement. The moon is constantly being measured by its environment photons, cosmic rays, gravitational interactions with Earth. It exists in a definite macroscopic state because it's perpetually decohering, constantly interacting with the rest of the universe in ways that suppress quantum superpositions and enforce classical behavior. Macroscopic objects don't exhibit quantum weirdness, not because they're fundamentally different, but because they're so thoroughly entangled with their environments that the quantum coherence necessary for superposition is destroyed almost instantly. You sitting there are made of quantum particles, but you're not in a superposition of being here and there because you're interacting with trillions upon trillions of air molecules photons, sound waves, gravitational fields. Those interactions measure you, collapse your wave function, force you into a definite state. The quantum world and the classical world aren't separate realms. They're the same world viewed at different scales, with different degrees of environmental entanglement. And this brings us to something I find both humbling and profound. Physics has given us incredible power. We can split atoms, we can create new elements, we can manipulate quantum states to build technologies that would have seemed like magic a century ago. But physics has also shown us the boundary of what can be understood. There are questions that have no answers, not because we haven't been clever enough to find them, but because the questions themselves rest on assumptions that nature does not honor. What is the electron doing when I'm not measuring it has no answer, because what it's doing presupposes a definite state that doesn't exist. Does the electron really go through both slits? Has no answer, because really assumes an objective reality independent of measurement that quantum mechanics denies. This is hard to accept. We want reality to be out there, definite and complete, waiting to be discovered. We want to believe that if we just measure carefully enough, think precisely enough, we'll eventually know everything. But quantum mechanics tells us that reality is not like that. There are irreducible probabilities. There are complementary descriptions that cannot be unified into a single picture. There are limits to knowledge that are written into the fabric of nature itself, and perhaps this is the deepest lesson of all. The universe is not obligated to make sense to us. It's not obligated to conform to our intuitions, our language, our categories. We've been extraordinarily fortunate that mathematics gives us a way to describe quantum phenomena with such precision, even when words fail us. The Schrödinger equation works. The uncertainty principle is exact. The predictions match experiments. But understanding the kind of visceral intuitive grasp we have of everyday objects may be forever out of reach. And that's not a tragedy. That's nature being honest with us about its complexity. I spent my life arguing with Einstein about this. He believed quantum mechanics was a temporary framework, a stopgap that would eventually be replaced by a deeper deterministic theory restoring the classical picture of reality. I still believe that quantum mechanics is revealing something fundamental, something final. Not final in the sense that there is nothing left to discover, but final in the sense that the indeterminacy, the complementarity, the role of measurements aren't artifacts of an incomplete theory. They're features of reality itself. And the evidence, as far as we can tell, supports that view. Bayes' theorem, developed decades after my debates with Einstein, showed that any theory trying to restore determinism with hidden variables would have to be non-local, would have to allow instantaneous influences across arbitrary distances. Experiments testing Bayes' inequalities have been performed thousands of times, and they consistently violate the predictions of local hidden variable theories. The correlations quantum mechanics predicts entangled particles influencing each other's measurements instantaneously, no matter how far apart, really occur. Nature really is non-local, or else it really is indeterminate, or both. Either way, the classical picture is dead. So where does that leave us? We have a theory that works brilliantly but defies comprehension. We have technology built on principles we can't visualize. We have experimental results that contradict every intuition evolution gave us for navigating the macroscopic world. And we have a choice. We can despair that nature refuses to make sense in familiar terms, or we can marvel that nature has shown us something so strange, so unexpected, that it forces us to expand our concept of what making sense even means. I choose marvel. I choose wonder. That's what quantum mechanics teaches beyond all the mathematics, beyond all the technology, beyond all the philosophical puzzles, is that reality is far richer than we ever imagined. The universe is not a clockwork mechanism running along predetermined tracks. It's a living tapestry of possibilities, crystallizing into actuality at each measurement, each interaction, each moment of observation. We are not detached spectators cataloging facts about an independent reality. We are participants in a cosmic process, and the questions we choose to ask, the measurements we choose to make, shape the answers we receive. That doesn't mean reality is arbitrary. The wave function constrains what's possible. the laws of quantum mechanics are just as strict and unforgiving as the laws of classical mechanics. More so in some ways because they forbid things classical physics permits. You cannot simultaneously know position and momentum. You cannot clone a quantum state. You cannot signal faster than light using entanglement. These aren't limitations of technology. These are laws of nature, as fundamental as the conservation of energy. But within those constraints, there's room for something we never expected. Genuine novelty. When the wave function collapses, when one possibility becomes real and others vanish, something new enters the world. Not something that violated the laws of physics. The probabilities were always there, encoded in the wave function. But which specific outcome occurred is not determined by any prior cause. It is random, in a sense, deeper than anything classical physics ever contemplated. And if you trace that back far enough, it means the universe itself is creative, constantly generating new facts that weren't implicit in its prior state. I don't know what to do with that realization, honestly. It's both exhilarating and unsettling. We've spent centuries trying to reduce everything to mechanism, to show that the present determines the future with iron necessity. And now physics itself tells us that's not how nature works. At the quantum level, the future is open. Probabilities are real. The dice God plays with aren't loaded. They're genuinely random. And that randomness, amplified through the chaos of molecular interactions and evolutionary processes, may be part of what makes the universe interesting, unpredictable, alive. Of course, I must be careful. I'm talking about atoms and electrons, not free will or consciousness. Those are different questions, and we must not confuse them. The fact that electrons are indeterminate doesn't immediately solve the problem of human agency. But it does show that the universe is not the deterministic prison that classical physics seem to describe. There's room, genuine physical room, for things to happen that weren't predetermined by the initial conditions of the Big Bang. Whether that room extends to human choices is a separate question, one I won't pretend to answer. But the possibility is there, in a way it never was under classical mechanics. What I can say is this. Quantum mechanics has taught me humility. It's taught me that nature is under no obligation to be comprehensible in human terms. It's taught me that the categories we use to organize experience, object, and property, cause and effect, here and there, now and then, are not fundamental features of reality, but tools our minds have developed for a specific purpose in a specific domain. And when we push beyond that domain, when we peer into the atomic world, those tools break down, not because we're using them wrong, but because they don't apply. And yet for all that, we've managed to understand something. We've built a mathematical framework that captures the essential strangeness that makes predictions we can test that works. We don't have a picture or visualizable mental model of what's really going on. But we have the equations, and the equations are enough. They tell us what we can measure, what we can predict, what we can build. They draw the boundary between the noble and the unknoble, and that, in the end, may be as close to truth as finite beings like us can never get. So when you imagine the atom, don't picture a tiny solar system. Don't imagine electrons tracing orbits through space. Imagine something stranger. Imagine a cloud of probability, a wave function that extends to all of space, collapsing into definiteness only when interrogated by measurement. Imagine complementary descriptions, wave and particle, position and momentum, each revealing part of the truth, each inadequate alone, both necessary together. Imagine a reality that doesn't exist in the way microscopic objects exist, a reality that becomes only when observed, that remains potential until actualized by interaction. And if that seems impossible, if it seems to violate logic and common sense and everything you know about how the world works good, that means you're beginning to understand, because the world doesn't work the way common sense suggests, not at the atomic scale, not at the foundation. And the fact that we've discovered this, that we've built a theory describing it, that we've harnessed it to create technology, that's one of the great achievements of human thought. But let's not forget the cost. We've gained power over the atom, yes. We've gained predictive accuracy, technological capability, mastery over nature at its smallest scales. But we've lost the comfort of comprehension. We've lost the illusion that reality is simple, intuitive, accessible to human understanding. And maybe that's the trade-off. Maybe to know nature deeply is to confront its strangeness, to accept that the universe is far more subtle than we ever imagined. I don't know if that's comforting or disturbing. Perhaps it's both. Complementarity, again, truth that contains its own opposite. What I do know is that this is where we are. Quantum mechanics works. The experiments confirm it. The technology relies on it. And the philosophical impetus, the limits of knowledge, the role of observation, the inadequacy of classical concepts are not side effects, they are central. They're telling us something profound about the nature of reality and our place within it. We are not observers standing outside nature, cataloging it from a position of detachment. We are participants, embedded in the very reality we are trying to understand. Our measurements are interactions. Our knowledge is partial. Our concepts are tools, useful in their domain but breaking down at the boundaries. And the quantum world, strange and paradoxical as it is, may be showing us what reality looks like when you stop imposing human categories on it and let nature speak for itself. That's what I've spent my life trying to articulate. Not that quantum mechanics is the final word. Science never stops, and there's always more to learn. But that the strangeness we've uncovered is real, fundamental, irreducible. The world at its smallest scale doesn't behave like the world of our experience. Energy doesn't flow smoothly. Particles don't have trajectories. Reality doesn't exist independent of observation, and those aren't failures of the theory. Those are discoveries about nature. So embrace the paradox. Accept the complementarity. Let go of the demand that reality makes sense in classical terms. Because once you do, once you stop trying to force quantum mechanics into a familiar framework and instead let it show you something new, you glimpse what I've seen. A universe far stranger, far richer, far more mysterious than anyone imagined. A universe where the opposite of a profound truth is another profound truth. A universe where knowing means accepting the limits of what can be known. And that, I think, is the biggest misconception of all. Not that energy flows in orbits, though it doesn't. Not that electrons have definite positions, though they don't. But that understanding means reducing everything to familiar, comfortable, classical terms. It doesn't. Sometimes understanding means recognizing that nature has shown you something genuinely new, something that transcends the categories you brought to the encounter, and having the courage to accept it, to work with it, to build on it, even when it refuses to make sense in the way you expect it. That's what physics has taught me. That's what quantum mechanics is. And that's why, more than a century after we started probing the atom, the mystery remains. Not because we failed to solve it, but because the mystery is the answer.